Okay, so good evening, everyone, and I hope we are having a great evening. Today, we are going to look at more of regression. We are going to look at logistic regression. And if we do have a bit more time, we'll also look at the linear regression using a polynomial function, right? So, so far with the linear regression that we did with single variable and with multiple variables, what we were doing was basically, first order dependencies or first order equation. So basically the x was always x raised to power 1, right? So x1 raised to power 1, x2 raised to power 1. It was always what we call the first order equation. Now, with polynomial, we bring in higher orders. So we bring in second order, third order, and so on and so forth. So we now start talking about x squared, x raised to power 3, x cubed, x raised to power 4, x raised to power 5, and all of that. So we have that as a polynomial because sometimes a polynomial is a better model for you to represent, a particular data set, right? And if you have an n order polynomial, that is a polynomial where the highest value of x can go up to, the power of n, or the highest term of n, or the highest order of n can go up to n, which is a high value. That allows you to be able to predict really complex relationships thing. So, but we'll start first with logistic regression. So when we say logistic regression, what is logistic regression? Logistic regression basically has to do with what we call binary outcomes, right? A binary outcome, basically the expected value is either true or false, either 1 or 0, right? Um, it is not a, a continuous range of numbers, right? It's not a continuous range of numbers, but rather it is just two possible outcomes. It's either yes or no. It's either 0 or 1. It's either white or black. It's either true or false, right? Where you just have two numbers. Of course, we have more. The extension of logistic regression is what we call classification. So classification, logistic regression is basically classification with two possible outcomes, right? But you could also have classification with multiple outcomes. So a good example of classification with multiple outcomes would be classification of red, green, blue, white, or classification of I don't know, maybe um, what do I use? Anything that has categories, right? Baby, child, um, teenager, adult, senior, right? So that's generally what we call classification. So logistic regression is a statistical method that you use for classification. It predicts the probability of a binary outcome. This is the most important thing that you need to understand here. It is predicting the probability of a binary outcome. And the binary outcome, like I said, is one of two possible outcomes, right? So you give it the inputs, just like in, linear regression or any other kind of regression, and then it calculates what the output will be. Now, typically, the way you do logistic regression is you use a kind of what we call an S curve or a sigmoid curve, right? It's a sigmoid curve, or it's also called a logistic curve. So I'll make some sketches kind of to explain what I mean when I say sigmoid or logistic, right? Basically, what this means is that if I were to, if it's a curve that kind of, when it is 0, when the x value is 0, sorry, when the x value is below a certain threshold, right? the y value will be 0, right? Then when the x value gets to that threshold, the y value begins to rapidly increase. And then just beyond that threshold, the y value rapidly jumps up and becomes 1. So that is, it's a very powerful relation that is used. Basically, you use it to convert data that is in the form of a continuous function. What I mean by continuous function is the value continues to increase, maybe linearly or something, right? But you want to convert that continuous function to a binary outcome, right? So you want to convert something that's continuous, like maybe starting from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? But you want to convert it to binary. You basically want to turn continuous information into categorical information. In this case, 2 categories. So, for example, if we were to say we want to classify people, generally into 2 sets based on their height, okay? You say you want to classify them based on their height. Then at some point, you have to decide the threshold. At which height do we begin to, change this classification, right? Or at which point do you, does somebody change from being a short person to a tall person, right? What is a height? What is a number? How do you define somebody that is short or somebody that is tall? This is the uh, important and interesting question, that we ask when we are talking about, um, you know, logistic regression. That's why we call it logistic. The reason why we call it logistic is this function that we are using to translate a continuous, term into a categorical term, right? That function is called a sigmoid function. It is also called, another name for it is the logistic function, okay? So when you do a logistic function, right, I'm going to show you examples. So you can already see here that you calculate that basically it's saying the probability, it's a probability function, but this equation here, 1 over 1 plus e raised to power minus z, where z is the input, right? Or x, I would use x as well. But yeah, so let's look at the sigmoid function. This is how it looks like. I'm going to open, let me plot this on a Jupyter notebook so that we will see how it looks like. So I'm going to start a new notebook and show you how this looks like. So the way I'm going to do this is I will, essentially, I'm going to plot this graph. So this is a logistic function, right? The logistic function is y equals 1 divided by 1 plus e exponent. Let's call it exponent minus x, right? It is an interesting curve, and you could ask yourself why. How did they come up with this? But I'm not going to go into the history of that. So first of all, I am, of course, as usual, we'll need to import NumPy, and we'll import matplotlib as well. Matplot. Okay, so let me run this just to be sure that we are getting our libraries correct. Okay. So this exponent, right? This exponent function, okay, matplotlib, matplotlib, yes. This exponent function, you could actually just do a plot of an exponent function. So let me show you what that looks like. With matplotlib, y equals to, let's just do this, okay? Y equals np dot array. So we're just going to get an array of numbers from, um, lists of range. Let's get 100 numbers. So I'm going to plot 100 numbers. By the way, this is X, not Y. So I'm going to get a range of 100 numbers. Then I'm going to calculate the Y of it, which is the exponent. So we just do np dot exponent, right? Or let's just plot it straight up. So plot dot plot X. So plot X, and then we'll plot. Well, the other thing is we could basically just yeah, okay. Let's plot X and then Y, which is np dot exponent of Y. So this is showing you how this, sorry, np dot exponent of X. So this is the same thing as just e raised to power X, right? So this is plotting. Let's talk a little about the sigmoid. Sigmoid is very important, so I'll just talk a little bit about it, or logistic function. So it starts off with being y equals, I need to figure out how to write this mathematically, but let me just paste this in here so it will be, let me just paste it in, right? So for those of us who did a little bit of maths, right, you will maybe have encountered it in one way or the other, and maybe you did not pay attention to it because you didn't think it was important, right? But here we are. We are here and it is important. So yeah, this is it. Um, so this is the function, right? 1 over 1 plus e raised to the power minus z. I normally like playing with functions like this so that I can have some intuitive understanding. I know we don't have enough time to do all of that. So I want to start off with e, just the e raised to the power x, which is the exponent of x, right? So that's why what I did was I took a range of 100 numbers, right? I then, let me make it easier to understand. I now have y equals to np dot exponent. So I'm now going to calculate exponent of those 100 numbers, right? Which is x, okay? Then I'm going to just plot it, right? So when I plot it, you now see something. The important thing you are going to see in this plot, I need to move this so that it will be more visible. Yes. So if you look at this plot, right, you will see this is it, right? It's going to have very low values until a certain point, and then it jumps up. Let's assume I'm not plotting 100. Maybe I'm plotting just 10, right? I'm plotting 10. Yeah, so it always looks like this. It always looks like this, right? It always looks like this. It always looks like this, like an elbow, kind of, a bent elbow, So you will see that it starts off very low for low values, but at a certain point, which we call the elbow, right? It turns around very fast and begins to move up. That's typically how the exponent x, function looks like, right? Now we will manipulate this exponent x function to kind of, give us that logistic function. And I want to get from the exponent x. The main thing with exponent x is it always starts very small, but at some point there's a threshold, it bends the elbow and it moves up really fast. If I change this to 20, I'm plotting 20 values, you still see the same thing. There's still an elbow, right? It's always going to look like this. There will always be an elbow when you plot it. I could even decide that I want to plot this as um, y scale. So I want to plot it as you know log, right? So this is a function actually, not a parameter. So I want to plot and make the y axis a log axis. It's always more interesting when you even look at it that way. Okay. So you can see that when you make the y-axis a log, it's a straight line. That's why it's called a logistic function, because log of a number is the opposite of e raised to power that number, kind of. So log of e raised to power x is equal to x. And so it always looks interesting this way. But yeah, I'm going to take this out, right? So you can see yeah, so you can see that. So no matter how the range is, you always have this elbow. So that's how we start off exponent x. Now we have exponent minus x. So exponent minus x will be flipping exponent x on the horizontal axis, right? So instead of calculating np dot exponent x, I will now negate x, right? And I plot it. So like I said, it becomes flipping the that logistic curve, the e raised to power x, that log curve, you flip it horizontally. So it's like putting a mirror in a vertical axis, and then it flips around. Okay. So that's the second step, right? That is this e raised to power minus z, or minus x for now. So that's np e raised to power minus x. Now, when you add one to it, what it means is when you add one to it, it jumps up by a value of one. So we add one to it, right? Which is the bottom of um this this formula here. It basically just lifts it up by one. So you see it lifts up by one. So that's cool. Right. Now, I can make this range even more. So we got to 20. I could make the range 200. It will still have the same shape, right? Except that the elbow will be sharper because the range is wider. So elbow is sharper and it comes up really early. Now, the last part of it is we will now reciprocate it. So we'll have the reciprocal of this, which is 1 divided by this. And when I do this, it will end up giving me this function, which is the logistic function. And you see that it has this value here, right? It goes from 0 to 1. And then at 1, it flattens out. I'm going to reduce this again because this 200 is too much. It's not allowing us to see the range. The range of the x values shouldn't really be that much, right? So you can see with range of x values, it actually starts from this 0.5 and it goes up. So the reciprocating it means I flipped it this time around on the I flipped it vertically, by think of it like I put a mirror this time around on the x-axis and I flipped it. So I now end up with this curve. This curve is the curve that says at this value of 1, okay, at this value of 1, you will never exceed the value of 1, by the way. It is proven. You can prove it by looking at the equation, right? Because as z increases, okay, e raised to power z reduces because it's a negative power. So as z increases to infinity, anything raised to power minus infinity goes to 0, right? So if it is 0 at infinity, the limit of infinity, it goes to 0. This will be 1/1. So the value will always be 1. It will never be greater than 1. Now, when z is 0 or z is 0, e raised to power 0 is 1. So the value when z is 0 is going to be half, which is what we have here, right? 0.5 at the value when. Now, when z becomes negative, which we don't have in our range, but I will now include the negative portion of the y-axis so that you see the entire curve, right? When z becomes negative, this becomes positive, right? So e becomes at infinity, at negative infinity, this is e raised to power positive infinity, which is a very high value. Oh, in fact, it's infinity. Anything raised to power a large number is a much larger number. And that number is so much larger than 1 that you can just take it as a very large number. 1 divided by a very large number is 0. So what it means is that as you approach the negative infinity, right, the value of this function becomes 0, but it will never get less than 0. It will never get negative because the lowest value it will get at infinity, the limit of infinity will be when this is very high. So the lowest value you will ever get will be 0. So we can experiment with that by, you know, changing this range function a little bit so that we start from -10, right? And we go to 10. We start from -10, we go to 10. So you now see, you now have two elbows. Interestingly, so you have two elbows. This elbow where it flips as it's approaching the maximum value of 1. And this elbow where it also bends as it's approaching the maximum value of 0. And then 0 is the threshold, the point where the value flips. So you will see that at this point, when it is very far away from the threshold 0, this becomes almost 1. And when it's very far away from the threshold in the opposite direction on the left-hand side, this value becomes 0. So there is a section of it, of course, in between here where the value can basically just not be exactly 0 or 1, right? This is a transition point. And in most cases, when you are doing logistic regression, you want to minimize this transition point. Because what we are doing essentially with this is that we want to convert a series of values, like I was saying, a continuous function, right? That starts from 0, and you want to map it. It starts from -10 or 0 or anything, by the way. And you want to, and it goes all the way to 10. No matter what value you have on this x scale, the value of y will always be either 0 or 1. It will always be either 0 or 1. So 0 will be here when it is on this side, okay? And 1 will be over there when it is on this side. So with the logistic function, you have successfully mapped numbers in any range into just two values, either 0 or 1. Of course, that is ignoring this middle part, like I said, which we'll talk about, because you'll be asking me, okay, what of these middle parts where the thing is not exactly 0 or 1? The values of y are swinging from point something to, from 0.1 to 0.9. You now tell me, oh, okay. So if you have converted, that means there's a certain range, right? There's a certain range where we will not get, so between this range, right, and this range, right, any values in there will not give you exactly 0 or 1. There will be somewhere in between. What we can then do is to sharpen this section, right? This middle section. And we can sharpen this middle section by applying constants, factors to the logistic equation, okay? And the kind of factors that you apply, you see that you can apply a factor to x, you can apply a factor up here, right? And you can also, well, you want to keep this one here. So if you apply a factor outside, you are going to expand the range. So it's going to be, instead of 0 to 1, it's going to be 0 to a higher, much higher value, right? If you apply a factor to x, so let's apply a factor called c, right? Minus c, instead of just minus x, we'll multiply x by a factor, so minus c times x. The minus has to still be has to affect, well, okay, that's still okay, minus c times x. So let's take c. We can try different values of c and see how it goes, right? So if c is 0, well, you won't get anything, you just get a straight line. If c is 1, that's the same thing as what we had before, right? If c is 2, you now begin to see interesting stuff, right? So the first thing you see is that this middle section becomes sharper, steeper, basically. So C is the factor that you can use to increase the steepness of this section to a point that the actual numbers that will pass through this section, the range of numbers that will pass through this section will be very small, right? So that's why sometimes you see in a lot of these logistic equations, you see this variable that will be, or this coefficient that will be placed next to the independent variable. So if C is a really large number like 300, okay, you see that it basically becomes what we call a step function, right? I'm even having an overflow because I'm doing an exponent on a really large number. So that is a logistic function. And I needed to explain this because it's the basis of everything when we talk of logistic regression. Now, again, let me restate that the reason why we have a logistic function is I want to be able to convert the independent variable, the x, whatever the x is, I want to convert it into just one of two values. Either it's going to be 1 or it's going to be 0, right? So let me draw this again. It's either going to be, apart from these ones that are in this middle section, right? Apart from these ones that are in this middle section, okay? But most of the values, when they are very far from that middle section, they will always be either 1 or 0. They will either be 0, right? Or they will be 1. That is why it's called a logistic function. And that's the purpose of a logistic function. You hear this word logistic, you hear this word logit, and a whole bunch of different other um, nomenclature. Okay, so let's go back now to looking at the rest of it. So logistic functions convert your linear output into a probability distribution. And like I said, that probability distribution is always going to be between 0 and 1, right? So for you to do logistic regression, we combine two elements. The first element is the linear part of it, what we call the linear predictor, okay? So the linear part of it is what you use to basically say, okay, convert your independent variable x, right? You add what we call a bias, okay? So remember, we already did this with linear regression. So you are basically doing the same thing as you did with linear regression. The first part, so you are going to use x, the independent variable, right, to predict a value of y. But when you have predicted the value of y, because the value of y can only be one of two values, it can only be true or false, it can only be 1 or 0, you have to then map that linear predictor through a logistic function to get what we call a probability distribution, right? That probability distribution is now going to give you, in machine learning or in statistics and probability, it is not actually the value that you're predicting, but rather it is the probability that what you are predicting is the value. So you need to think about it that way, right? So if I pass this through a probability distribution, I am not saying that the outcome is the actual value. Rather, I'm saying that the outcome is a probability that it is the actual value. It is good to think about it that way because it then helps you to generalize this logistic regression, this simple principle, to any classification problem. Now, for now, though, we are going to just say, okay, let's assume our values can be either 0 or 1. It cannot be anything else. Then the logistic regression, sorry, the logistic equation is going to convert whatever we predict into either a 0 or a 1. Then we will now do training based on that. So that's the thing. Let me again show you how this looks like on a curve. I'm going to basically just plot this again so that you can see how it looks like. So right here, let's go back to the Colab. So now we have the logistic equation. Let's start off with the linear part of it, right? So again, we have numbers and we have the basic linear equation, right? Which we can call it Z. So we want to use Z because Z is an intermediate value. It's not the final value, right? It's not the final value, it's an intermediate value. So we now have Z equals M times X plus C. It's basically the same thing, right? Z equals M times X plus C. So we can have our M and our C as having any values, right? But for now. So that's the first part, the linear part of the logistic equation. Then the logistic part of it, where you convert this intermediate value into what we call logits, right? You put it through the logistic equation. So remember, we have already said the logistic equation is 1 divided by 1 plus exponent of minus z. And that is what will give you your y. So your y is now going to be values that basically have a logistic, plot. Let's do this. We have, let me just kind of add a plot then of linear versus logistic. So I'm going to do, in this, I'm going to do a plot figure, let's have that fig size, and then plot dot subplot. Okay, so we start 1 to 1, right? And then subplot 1 to 2. We will plot logistics. So we can see the difference. Then I'm going to bring this up in here. Okay, let me do this down so that we'll have a separate thing. Okay. And then let me revert this to what we had before. Okay, so here, I'll still do the same thing I did before. I'm going to take X as an array of numbers that start from -10 to 10. I'm not going to use M and C for now. Okay, I am going to use M and C. So I will just now plot Z. It will be a linear function. So because it's a linear function, I'm going to give M and C some values, right? So maybe just 4 and C is 3. Okay. So Z is now going to be the intermediate plot, which is going to be linear, right? And then Y will be the logistic plot, which we will also do. So I can now run this. You can now see that here, this is a plot of a linear function. This is what we were doing last week and on Monday, basically a linear plot. But now I take this linear plot and I pass it through the logistic function, and this is what I get. Okay. Oh, there's one thing here. Yeah, that's so this is what I get. And you can see that no matter how high the value of y is, it always gets, no matter how high the value of z, which is the intermediate value, no matter how high it gets, it always gets mapped to 1 on the y-axis, right? No matter how low the intermediate value is, the z, it always gets mapped to 0. That's what's going on here. You can see that here it's almost minus 40, right? But it's mapped to 0. And here is 40 and it's mapped to 1. So logistic function basically means that if I don't plot the intermediate value, all the x values, I map it between, 0 and 1, right? With most of the values on extremities being either 1 or 0. And then you have a certain transition section here where the values can switch, are moving from 0 to 1. So that is logistic curve, and that's a logistic equation. Now, when you have this logistic equation, the next question you'll be asking is, how do I calculate the cost function? That's the next important thing. You need to be able to calculate the cost function. And to calculate the cost function, we use an equation called the negative log likelihood, or binary cross entropy. This looks like an interesting, it looks like an interesting, very complicated, very complicated equation, right? But I can make this very simple to understand. It's not hard. I can tell you how this equation was derived. And this is how this equation was derived. So first of all, they basically came up with this, think of it as an if statement. So remember, we have two possible ways that you can look at, two possible outcomes rather, right? The two possible outcomes are either you're either having a 0 or a 1. Those are the two possible outcomes, right? So now, what we do to derive this equation is when x is above the threshold, okay, we take 0. Sorry, we take 1. And when x is below the threshold, we take 0. So again, let me draw this. This is the function. Okay. I think I need to do a better job of sketching it, but yeah. So this is how it basically looks like. That wasn't a really good one, but this is the threshold. So this is the threshold. You can consider it this way. So what we are saying is above this threshold on this side, right, the value is always going to be 1. And below this threshold on this side, the value is always going to be 0. So that's the first, that's the first intuition around it. Now, the next thing we do is, if that's the case, that means what we are saying is that if x is greater than the threshold, in this case, let's assume that the threshold is 0 for now. So if x is greater than 0, then the value is then what? Y equals to 1. That's basically that's the basis of it. If x is equals to 0, then y is 1, right? That's what we are saying. Then if x is less than 0, okay, then y is what? 0. That's basically what this is. That's the logistic function. Of course, like I said, just for the moment, ignore that transition section, okay? Ignore that transition section where the thing is moving from 0 to 1. Now, what that means is when you look at this, they have basically come up with an equation that allows you to do that. Basically by saying this part, and then this part. So let's look at these two parts separately. Okay. So the first part is, remember I just did a log plot. A log plot. Okay. So ln of P1, right? Where P1 is a sigmoid. So by the way, I did not complete this thing. So let me explain to you that this sigma Z, this is sigma. This is a Greek letter sigma. It matches to S, right? This is the lowercase version of sigma, the uppercase version, which we have been using to mean summation, right? This is sigma uppercase, capitals. It means summation. Sigma lowercase. It basically, in this context, is used to represent the sigmoid function. That is called sigmoid function. It comes from the Greek letter sigma, right? So you can go Google what sigma means, right? So anytime you see this, right, it means the sigmoid function of anything z, right? So the sigmoid function of z will always be between 0 and 1. And if you look at this other thing, it says the probability that y is equal to 1 given x. The probability that y is true given x. That this bar here means given. It means given. In other words, if you are given a value of x, what's the probability that y equals to 1? Right? Of course, the probability that y equals to 1. What is the, if a probability of that y equals to 1 is something. I don't want to use any letter. Just what is the probability that y, okay, let's say p. Yeah, that's why we're using p here, right? The p function, which is a probability. So if the probability, right, that y equals to 1, if the probability that y equals to 1 is, remember, probability is always from 0 to 1. So essentially, sigmoid function allows you to map your outcome to a probabilistic um, um, space, right? A probabilistic space, data space, basically. So if the probability that something equals to 1, if the probability is 0.8, then from simple law of probability, what is the probability that that thing is not 1? The probability that y is not equals to 1 will be what? 0.2, because the probabilities must add up. Remember, there are only two possible outcomes. It's either 0 or 1. So if the probability of it being 1 is 8, is 0.8, then the probability of it not being 1 is the remaining probability, which is 0.2. Okay? Take note of that. It's very important. Or let me change this so it's easy to understand. If the probability that the color of, so let's use two different, a different thing entirely to avoid confusion, right? Let's assume that we are saying that the probability that the color, we only have two outcomes. It is either red or it is not red. It is either red or it is not red. The probability that it is red, okay, if the probability that y is red is 0.8, then the probability that y is not red is what? 0.2. Okay? This is very important because then you understand why we have arrived at this function here. The probability, right, that y is not red, okay? Let's put it using the equation. Pardon me, my, okay. It looks a bit off. Let me see if I can write straight rather than writing curve. So if the probability that y, if the probability that y, okay, the probability that y is red, probability that y is red, right? Or let me put it this way. Probability that y is not red is equal to the it's equal to 1 minus the probability that y is red. This is very important. Very important. You already see yi and 1 minus yi. So that already tells you where we are getting this, right? Then you also see pi and 1 minus pi. So we are talking about reverse probabilities here, okay? So I hope we are following. If you're not following, raise up your hand and ask a question that will bring you close. Right, so we're talking probability. So a probability that something in a two binary classification is binary classification, basically, right? So the probability, if the probability of one outcome is equal to 1 minus probability of the other outcome, since there are just two outcomes, this is the most important thing. Now, let me clear this board and now explain how we arrive at this equation. So the simple thing is this. If the probability, let's assign the value of the probability. Let's, instead of doing all that long thing, let's just say probability is pi. So this probability pi is the same thing as the probability for each data point that the value, your expected value, is red, is the expected outcome, right? Then what it means is that let's it means, what it means is that at the point, right, if you want to calculate the cost function, now let's assume that the model does a prediction. Okay, if you look at this whole chain of equations, right, the prediction is equals to a linear function, right, that comes from x times the weight or the parameter plus the bias. Okay, there's a transpose here, and I can explain the transpose later on. This is very interesting because this is the same equation for neural networks, and we are going to see it later on. In fact, in neural network, this sigmoid function is what we call an activation function, but we'll talk about that later. So now this P is a probability, right? And you have calculated it as a sigmoid function. So let me use a sigma. You have calculated it as a sigmoid function of Z, right? Where Z is the intermediate value, basically this linear value. So that gives you a sigmoid curve, right? So the probability that, let's assume you have done a prediction, okay? Your prediction can only have one of two values, okay? It can either be true, sorry, it can either be true. Let's use true. It can either be true, which means it is correct, or it can be false, which means it is not correct. Your prediction can only be that it is what you wanted to predict, or it is not. So again, let me clarify that. Let's assume that the data, we have given data to the model and I want it to predict whether the color is red or not. If it predicts red, that means it is true, so it is correct. And the probability that it is predicting red, or it's predicting that probably that it is red, right? The higher that probability of the prediction, the closer it is to 1, right? So that's true. If it is not predicting red, then it is false. Now, if we take this sigmoid function and we throw in any number, again, let me draw the curve. You are going to have something like this. So if we now look at your y hat, right, your y hat for a given x, right, your y hat is always going to be between 0 and 1. Now, in this section where it is moving, the closer it is to 1, the better the prediction, right? The further away it is to 1, it is from 1, the lower the prediction. That's where we are getting this function from, where we are saying that if I take my predicted value, right, and its value is above this threshold, which is 0.5, since 0.5 is the halfway point. If I now multiply it, right, let me correct this, right? This y is not the y hat, right? yi is the actual value, what you want it to predict. Then, so this is yi, the value I want to predict. If I now multiply it by p, ln p, ln pi, remember pi is the prediction. It's the prediction. So remember that, but it is in the logit space. So it's probabilistic. It's 0 to 1. Pi is a prediction, yi is the actual value. So if yi, which is the actual value, if it is 1, then the then this will be 1 times ln pi. Ln pi is not going to be, ln pi will be 0 if it is perfect. Ln pi, ln 1, which is log of 1, right, is what? 0. And log of 0 is what? Log of 0 is -1. Um,
Undefined.
is infinite. Oh, I wanted to say infinite. Okay, but we'll come to that. So you have, yeah, log of 0 is infinite. It's a very big, is minus infinite actually. It's a very big number. So this is the first part of this, right? This is the first part of this equation. Now the second part of this equation, you now minus it. So what this means essentially is that, let's take a single point on this curve. I think I need to get a better curve, but let me see if I can just manage this one so that we can understand. Let's take any single random point, right? Blue, and we put it here, right? So this value, remember this logistic curve is the curve that maps my x value to my y value. So the logistic curve, the prediction will always be on this logistic curve. The prediction will always be on this logistic curve. But let's assume that for this prediction here, the actual value is 1, right? Remember, there are only 2 possible actual values, either 1 or 0. So if the actual value is 1, right, the other actual value is 0. Now, if the actual value is 1, then, and I predict 1, what is my error? If the actual value is 1 and I predict 1, how is my error, large or small? You can type in the chat. If the actual value is 1 and I predict 1, then the error is small. In fact, the error is 0, because that's basically, it's 0. If I predict exactly 1, the error is 0. And so that's why ln of 1 is 0. So basically what we are saying is that by taking the log, the natural log of the prediction, right, we will always get a value that is close. So for the situation where y, the predicted value is 1, right, the cost function is natural log. Okay, I'm not really writing this well, so I will rewrite this. So we have 2 situations, we have 2 cases. Case one is where the actual value is 1. So when the actual value is 1, right, the error, right, the error for y equals to 1, the error, the cost function, in this case, we use L in logistic regression. We don't use J, we use L. So we are saying that the cost function, L, is going to be ln of the prediction, P. Why? Because think about it. If y is 1 and my prediction is 1, then the cost function ln of 1 is 0, right? Or log of 1 is 0. So that means I'm perfect. But if my prediction is 0.9, which is not exactly 1, right? 0.9 is going to be a negative value, okay? But it's going to be a negative value that is close to 0, right? It's going to be close to 0. So, and that's why it's called negative log likelihood. For you to get the actual cost function, you have to negate that, because you're taking a log and the values that you're taking logs of are between 0 and 1. In fact, let me go plot this up so that it's easier for me to explain. I might end up spending the whole day just explaining the cost functions, but it's probably a good thing, right? So give me a second. Let me put this in my let me put this in Jupyter Notebook. It's always easier to do this in Jupyter Notebook. So I'll take this and I'll break it into its component parts so that we can understand, right, the cost function. So yeah, I'll put this up here. By the way, for those who are wondering what this is, I'm basically pasting an image that I screen grabbed here, and the image is giving me the base 64 encoding of that image instead of giving me a URL. So this is one very nice feature that it has. It allows you to just paste an image. This is a base 64 encoding of that image, and it shows you the image actually. So cost function for logistic regression, which is what we call negative log likelihood, negative log. And I'm going to explain where this name comes from, likelihood, right? It's negative log likelihood. It's basically the likelihood based on a negative log function. So let's start first. The first part of this is um, when the actual value is 1, right? But before this, let us plot a graph of ln p, right? So we take actual values to be any value. We can take np.random. So let's assume the predicted values, right? We can do a predicted value array here, np.random, okay, of um yeah, np.random. I would like to specify okay, np.random.random and I want to get like 10 values, okay? So we just do that and let's just plot it, you know, in a matplotlib plot, not a histogram. I'm just going to plot plots dot plot. Yeah, we're just going to plot p. So yeah, well, we can do this. So yeah, so you're going to see that. So this is random plot of you know, probability values. Okay. Now, let's do something now. Okay. We're going to plot, this is a probability value. We're now going to plot the log of the probability value against the probability value itself, right? So we will do np dot log. Okay. In programming, there's nothing like lin, right? You won't see lin. You see log. So whenever you see log, this log is actually log to base 2. But if you want log to base 10, you actually see log 10 and you know a bunch of other logs. So we'll plot log p, and I'm going to make this a curve. So you will see how it looks like. Okay, this looks interesting. Um, let's make a scatter. Let's make a scatter plot. Right. So it looks better because I was picking random values instead of sequential. But whatever is the case, you can see that this this value is let me print the values so I can as well see print p let me print zip of p and np log p. So we'll see how it looks like. Okay, it needs to be a list, print list, zip. Okay, it doesn't look too nice. Um, yeah, uh, okay, let me just print them separately. P and Right. So now I'm printing the two values so you can see them. So you have the P and then you have the log of the P's. And you see them forming a kind of curve. This curve actually is very simply a log curve. If I wanted to draw a line around it, this line would be, yeah, it would be something like this. Basically, of course, my hands are crooked, but that's how that line is. That's a curve of a log. That's a log curve. Okay, so it's very important to understand that. Now, um, okay, so this is a log plot. Now, the question is this. We will transform this to see how this works. You can see that if P is close to 1, then we'll have a value of 0. And if P is far from 1, is close to 0, then we have a value that is a negative value. The closer it is to 0, the more negative it is until it gets to negative infinity, right? So I could also plot a separate graph instead of, I wanted to do a range, but let's do something like this. Let's do a range, okay? Let's do a range of values that starts from 0 and end at 1. Or let's say it starts at 0 and ends at 100. And steps are, yeah, 100 values. And then we divide this by 100 so that we are going to actually get, instead of random values, we're just going to get a range. Oh, I'm sorry. np.array range. So we will do this. Yes. So we have 100 values. So you can see that where you have 0, we have minus infinity. So this is basically the lower end. And then where we have 0.99, where it didn't get to 1, you now have a value that is close to 0. Now, if I were to, let me make this go up to 1. So let it go up to 1. So where it is 1, right here, you see that it has a value of 0. So this is the plot, okay? This is a log plot. Now, how do I use this to bring about the cost function? What we are saying essentially is that if the prediction is close to 0, right, it's close to 1 rather, if the value of the prediction is close to 1, then, and the expected value, the true value is 1, then the error is 0. But this is a situation where the the expected or the real value is 1. In this scenario, as it goes further away from 1, as the predicted value rather begins to slip away from 1 and begins to kind of go away from 1, right? As it begins to go away from 1, then you have a situation where as it begins to go away from 1, the error becomes higher and higher, but in a negative direction. Okay, so you can see as it is going towards 0 from 1 on the y-axis, as it is going towards 0, right? You see that the error is increasing, right? It's increasing, and at 0 the error is infinite, right? So for you to now get, you use this as a measure. So by the time you apply a negative sign to it, you essentially flip it. And that negative sign will now give you a measure of the error in the positive direction. That's why it's called negative log likelihood. It's like log likelihood because we are using log function to calculate the likelihood. Likelihood is a probability. We're effectively calculating the probability that this value is 1. That's the first one. The probability that this value is 1. So you will see that when the value is 0, the error is higher. But when the value is 1, the error is lower. And when the value is exactly 1, the error is 0. That's the first part of that equation. And you can already see that equation is minus np dot log p. So you then multiply it by yi, which is 1 in this case. And I'll explain to you why you have to multiply it by 1. Now, the second part of it is I want to calculate the likelihood that it is not 1. You know, how much does it cost? How much does it contribute to the cost? You know, so you do the reverse, right? If it is not 1, then you are basically, remember what we say, the probability, if the probability of something being 1 or yes is 0.8, the probability of it not being 1 or yes is 1 minus 0.8. So the other part of this is to subtract it from 1. Okay, and you do the same thing, right? So if we plot P against 1 minus P, we now have this other curve, right? We are plotting it against the log of 1 minus P, which is this other one, right? And you can see that in this case, the error continues to increase as it is away from not 1. So this is now calculating the cost function. How far away is it from being the opposite of 1, right? Which is 0. So to now combine these two to get the total cost function, we'll now say, okay, when it is 1, give me the probability or the cost when it is 1. That's why you multiply it by yi, because yi is 1. So 1 times ln p1 will give you ln p1, right? While 1 minus yi, if yi is 1, then 1 minus yi is what? 1 minus 1, which is 0. And 0 times this opposite probability will give you 0. So you will now only be measuring the cost of it being far away from 1. Remember when we're talking about mean square error, we said we want to compound the errors. We don't want the negative to cancel out the positive. It is the same principle here. When it is 1, or when it's close to 1, or when the expected value is 1, I want to take this part of it. I want to take this error. But when the expected value is 0, I want to take this error. That's basically what it is. Because if not, by the time you add this and this without applying those, you get zeros. And it's very easy to see that. I can give you another, code block that has plotting the two of them minus np, right, log np log p, right? And then we add it, which is plus minus is minus. 1 minus this. You'll find that your error will cancel out. And you're basically going to have, well, okay, it doesn't cancel out, right? But you have this thing here. But it is not correct because what it means is that, well, this will be the composite error. But the thing is that when I want to predict 1.0, if I predicted 1.0, if the actual value is 1.0 and I predicted 1.0, I don't want a high error. I want a 0 error. So we will eliminate. So for us to eliminate, right, we will have to multiply by the actual prediction, the actual value rather, the y, right? So let me say y, which should be the actual prediction. So this is how we are able to arrive at this equation, right? We are basically saying that when I want the model to predict 1, I want to use this. So I use the 1, that same 1. I use it to allow this. It's like a gate. I allow this in and I block this error term from coming in, but I allow this error term. And the way I block this is by 1 minus 1, which is 0. So it's going to take this one out, and I'm only going to see this term, right? That is the first part of it, okay? The second part is, okay, if what I want to predict is a 0. So this is when I want to predict 1. I don't want this term to be part of the cost, function. So I only take this. But when I want to predict a 0, if the actual value is 0, and that's what I want to predict, then I don't want this function. I want to cross this out, and this one rather will come true. Because if I want to predict a 0, the ln 1 minus pi is what gives me the correct cost. Because ln 1 minus pi, if you look at the graph, you will see ln 1 minus pi. This is ln 1 minus pi. So 0 is closer, right? If the value is 0, if the prediction is 0, the error is 0. So I want to use this error function when I am trying to predict 0. But I want to use this error function when I'm trying to predict 1. It is what we call a piecewise equation. Piecewise in the sense that you are taking two pieces of an equation or two different equations and you are combining them, but you are combining them based on conditions, right? So let me again say it. When I want to predict 1, I want to use this loss function. I want to use the first loss function, which is this one. But when I want to predict 0, that's this one. I want to use this one, and I don't want this one. But when I want to predict 0, I want to use this other loss function, but I don't want to use the first one. So these terms here basically help us to do the elimination. When I want to predict 1, right, this one will go through, and this one will be crossed off because 1 minus 1 is 0. But when I want to predict 0, right, I don't want to use this one. I want to use this function to predict 0, and I don't want this one to apply. So this yi will be 0. 0 times this, it will cancel it off, but 1 minus 0 is 1. So I'll end up using this function. That is basically spending 30 minutes to explain the logistic, what we call the cross entropy or negative log likelihood. That is how it was arrived at. I basically want to explain that is how it was arrived at. So now, having explained that that is a cost function, and that's the best cost function you use for logistic regression, because it's always going to give you values not based on the actual numeric value, but rather on how close it is to 1 or 0 based on what you wanted to predict. Okay, that is NLL, negative log likelihood, or cross entropy. So they say that they say the loss is convex in W. The loss is convex. Okay. So having done that, that is the loss function. Remember, there are 3 steps. First step is the function you use to predict. So we have come up with the sigmoid function, right? That is the prediction function, right? That's the model. The model is the function that you use to predict. So in this case, it's a sigmoid that is applied to a standard linear predictor. That's the first. The second is the loss function, which is the negative log likelihood or the binary cross entropy, right? That's the second function. Now, the third one is the gradient. You need to calculate the gradient of this negative log likelihood. It's actually not that hard, but I won't go into it because we've more or less run out of time. And but I'll show you what it looks like. So this gradient function is what you would then use to determine how to do. We'll look at the gradients here shortly. So, but the methods you use to fit or optimize logistic regression, we have what we call batch gradient descent. Batch gradient descent is basically the standard gradient descent, where you take all the data points, you calculate the total loss, right, using the cost function, and then you use that grade, you compute the gradient based on all of those data points, and then you use that gradient to do your update. Okay, that is batch gradient descent. But we also have what we call stochastic gradient descent. The reason why we use stochastic gradient descent is batch gradient descent is not very, very tenable. It's very slow on very large data sets because you are calculating the loss or the cost function of all the data points. So assuming that you have a data set that has 10 million data points, 10 million rows or records or samples, right? So you are going to calculate this log function for 10 million data points. That can be very slow, especially you have to calculate each time now. Remember, you have to calculate each time, then you calculate the cost, then you calculate gradient, right? And then use the gradient to do gradient descent, which is the batch gradient descent. So 10 million is a lot. It is going to be very slow for you to calculate your loss and your gradient to be able to train your model. So we come up with what we call stochastic gradient descent. So in stochastic gradient descent, you are not taking the entire batch, all of the samples. You are not taking all the 10 million. Rather, you take small sub batches or sub sections or sub samples of that 10 million. You can take maybe 10,000 instead, right? So you take 10,000 and you calculate the cost based on the 10,000. You train, you fit it to that 10,000, and then the next time you take another 10,000, right? So, and this sampling is sometimes random. So it's more or less based, the stochastic gradient descent is based on this principle of if you can take a representative sample and you train your model based on it, it will come close to the entire batch, right? But you do need to sample from different portions of the batch. You can only sample from one subset or subsection of the batch because you're going to have what we call overfitting. You're going to overfit to only that subset of the batch that you have used. So you have to sample across different subsets, right? And continue to train your model. So that's what we call stochastic gradient descent. It gives a faster convergence because you are not, because of the speed of calculating smaller, subsamples versus the entire batch of 10 million, noisier because when you take a subsample, the cost or the error might be small. You train on that, right? The model becomes very good and can predict that. Then you move to another subsample. When you bring that subsample to train, you'll find that the model, the error increases because the model always optimizes to the sample that you give to it to train at a given time. But by the time you take another sample, it will have a higher error than it had before. And then you train it on it, it becomes better. And then after that, you go to another subsample, right? So you are going to keep having this jumpy loss curve where it goes down, right? While you're training on a given sample, when you switch to another sample, the loss will jump up again and goes down again, and then loss will jump up again and go down again, and it keeps going that way. But after some time, you would have trained the model so well it can fit well on all the data. It generalizes well on all the data. So at that point, your average loss continues to reduce. So that's stochastic gradient descent. You have other ones. We have what we call mini batch gradient descent, which is in between stochastic gradient descent and sorry, okay, I made a mistake. Stochastic gradient descent is where you are actually training on one sample at a time. One sample at a time, right? Rather than picking all of the samples. But I wouldn't say one sample at a time, maybe a small batch of samples. Then the mini batch gradient descent is you have small batches, right? Rather than large batches. So the difference between batch gradient descent, stochastic gradient descent, and mini batch is really just the number of samples that you use for each epoch. In the batch gradient descent, you are using all the samples in your data set. For stochastic is the other opposite, where you're using one sample at a time, right? To train one at a time to train. Then mini batch is where it's in between. That's really what I was explaining, where you take smaller sub batches and then you go across the entire batch. You have other ones. You have an IRLS rather, or Newton, what we call the iteratively reweighted least squares. So this is just a second order equation, second order information using the Hessian function, and it usually will converge faster, right? But it's more expensive per step. What I mean by that is it takes longer to calculate this Hessian of the batch, right? So it's basically equivalent to what we call a Newton-Raphson. Well, Newton-Raphson, it's is the update function, right? Then we have quasi-Newton, we have coordinate descent, right? Quasi-Newton is basically an approximate to the Hessian method. It's faster convergence, right? Especially for medium scale problems. Then we have coordinate descent, which is used in some solvers for what we call L1 regularization. We'll talk about regularization later on. We'll talk about L1, L2, and the rest. Then trust region methods, conjugate gradient. These are less common, but they are still available. Then you have what we call one versus rest or softmax. So softmax is used for multi-class where you don't have just a true or false value, only binary, but you have multiple categories or classes, right? So these ones are solved, you use softmax. So the softmax helps you to kind of versus one hot, right? You use softmax to get a gradual distribution of probability of each of the classes. So it helps you to normalize, basically normalizes the cost function, to be between 0 and 1. Then we have regularization, which is commonly used, right, to stabilize the changes in your gradient, right? We'll talk about regularization much later on. So we now come to the gradient, the functions or the formulas that we will use, right? So like I said, for the logistic regression, the prediction is a sigma function. The key thing is this sigma here, right? It's a sigma function of xw, where x, of course, is the independent variable, right? And w are the coefficients or the weights or the parameters, right? This is a vectorized form of that equation, which I had shown you before. Basically, this is a vectorized form of y equals mx plus c for multiple x's and multiple, for multiple x's, right? And multiple m's, right? So by the time you vectorize it, you are going to have it basically as xw. I tried to do that last time. So this gives you the prediction. You're basically taking a linear function, a simple linear equation. You pass it through a sigmoid to get the classification between 0 and 1. Then the loss function is the negative log likelihood, which that's why we have a negative sign here, because log of these values, the values are between 0 and 1. The log of 0 is a negative infinity, a very high, large negative number, and the log of 1 is 0. So you're always going to have negative numbers. And we flip it. So by applying the negative sign, we now have positive values to represent the cost function, because the cost always has to be a positive number, where the higher the number is, the further away from what we wanted to predict. So you now have y transpose ln p. So we already said that it's y ln p for the positive predictions, while 1 minus y ln 1 minus p is for the negative prediction. So when I am predicting, the expected value is positive, or is 1 rather, I use this ln p. But when the value I wanted to predict is 0, I use ln 1 minus p. So this combines those two in a piecewise, those two piecewise into a single equation. Then the gradient, right? So this is where we talk of gradient. Basically, because this is a piecewise equation, we'll also do the derivative, on each term separately. And it's very easy. So if you do the derivative, you will find that 1 over n still remains as 1 over n. When you do the derivative of p, right? The gradient of log of p is 1 over, right? So by the time you do that, and then you do that, this 1 minus p, you're also going to get essentially this gradient, which is 1 over n times x times p, which is the predicted probability, minus y, which is the actual value that we want. And then you can add lambda omega for L2 regularization. I'm going to talk about L2 regularization later on. Lambda is typically a factor, a constant that you use to determine how much regularization you use. This is a Hessian version, right? The Hessian which you can use, right? And this is 1 over n xt rx, where r is a diagonal matrix, right? Of the probability times 1 minus the probability, right? Which is the prediction. Okay. So most of the time we are going to use this function. Um, I'm going to look for material that explains this if you want to go into all of this, but we don't really need to go into all of the maths. I just really like to explain it. The steps are the same, right? The only thing that has changed are the functions that you use. So while the maths and the function may seem very daunting, one thing I want to tell you is you don't really need to worry about it as long as you know the correct function to use. But it's the same steps. The first step is you prepare your data. You have to add a bias term, right? This is if we are doing if we are using vectorized approach, right? Um, but I think I'll look at just doing a simple logistic regression using maybe 1 or 2 variables. So we don't need to worry about vectorization yet. We will have to do vectorization as a separate class. Then you can do a one-hot encoding of categorical features. One-hot encoding is a way of basically encoding categories, especially if there are multiple categories. So what is one-hot? It means that every category will have a value of 0, except the one that is a correct category. The one that is a correct category will have a value of 1. And that's the one you want to predict correctly. That's what one-hot is. We are going to look at it, but for a binary classification, we are not going to use one-hot. We are just basically going to use 0 and 1. Then all of these other ones, we'll talk about them in detail. So the first thing is prepare the data. Then you initialize your weights. Typically, you can initialize them to 0, but sometimes it's good to have a small random number to initialize. Then you choose your learning rate or step size, which is what we've done already. Then you choose your optimizer. So we can use plain gradient descent or batch gradient descent. We can use a stochastic gradient descent. We can use a mini batch gradient descent. We can use adaptive momentum, which is ADAM, kind of gradient descent. ADAM is also a kind of gradient descent. It basically comes from it, but it uses what we call momentum, which keeps track of how fast the gradient descent how far the gradient has been changing. It has automatic learning rate, so you don't really use learning rates with Adam because it kind of has an internal way of tracking the learning rate. We can look at that in detail. We have momentum as well. You can choose regularization, but we'll not do regularization this time around. So the step is you now do the iterative update, which is you calculate the logits, then you calculate the probability, which is a sigma function, which is the sigmoid function, and then you compute the gradient, which is based on that gradient function that I'll give to you, and then you do the update as usual. Okay, that is the same thing that we do, and then we have what we call stopping condition, but we'll just use a number of epochs, and um, that is it. Let's go and do a little bit of this logistic regression, right? Using gradient descent, the standard gradient descent. So let's start off by, I'm going to just create a XY values, okay? Um, so the first thing is XY value. So X, let's just take random values, okay? So NP, um, yeah, random values for X. So this is X. It's just a list of numbers from 1 to 100. These numbers could be like, placement, position, or whatever. These are random, so we will see how well our, prediction does. Now, for Y, we will calculate Y by just using randomized value. And we are just going to calculate size. It's 100 samples, right? Um, um, so if the value of y is greater than is greater than is greater than 0.5. So if the value is greater than 0.5, then it will be true, right? If not, it will be false. So you can now see it's giving me true and false. So what I want to do is let me convert it to actual numbers. Okay, well, we can still leave this as is, right? So what we are saying is that when x is 0, I want you to predict true. When it's 1, I want you to predict true. When it's 2, predict true. And when it is not, I predict false. So I could plot this, but remember we are dealing with numbers. So I have to convert the y into actual numbers, zeros or ones. That is so I could do, yes, I'll just convert it to an int, okay? And right. So we can now do a plot, simple plot first. Let's plot the values. So first of all, this was just me generating values for x and y, random values. I could put this in a function, but let's keep going. So plot the values of x and y. So yeah, so this is, it's very easy to see this. Um, okay, yes, I have to choose the same dimension, same size. Okay, so you can now see the distribution is always either ones or zeros. Okay, it's always either ones or zeros. Another nice way I could do this would be to use some kind of you know, graphic, like a heat map or something, to tell you, okay, when these are the ones that are, you know, true and these are the ones that are false. But for now, let's just look at it this way. So what this means is that some of the y values are, you know, true, and some of the um, y values are false, depending on the x value. Now, that is the those are the values. Those are the data points that we want to predict. The next thing is we will now do the model function, which is the function that we want to use to predict. And this model function, we can now define it as y, right, or y hat of x, okay, x, and yeah, it's just going to be a single. So the thing is, this is going to be a system of linear equations because we have multiple y's that we want to predict for each x, okay? So but let's just use a simple m and c, okay? That gives us the parameters. So this is just going to be, let me bring this here so that we can see. The function that we will use to predict is the complete sigmoid of the linear equation. So we can say sigmoid of the linear equation, which is mx plus c, right? Then of course we define sigmoid. So I didn't mention this, but yeah, so I define sigmoid, which is a sigmoid function. Remember I said it's 1 over 1 plus np exponent minus x, okay? So we now have predicted values. So the interesting thing is we can now try with this. Let's predict and see what the prediction is giving us. And we can even plot it. So we can say y hat equals y hat, right? X So we have, let's say M and C, our initial values are 0.5, 0.5. So we predict with M and C. And then we can see Y hat. I need to run this. Then we can see Y hat. So yes, this is Y hat predicting with a basic sigmoid function. Now let's plot Y against Y hat just to show you how well our prediction is doing. Okay, ELT dot plot Y and Y hat. We can do it with scatter points. Right. So this is the Y value and this is the Y hat. Typically, we should have a situation where when Y is 1, Y hat should also be 1. So we'll have all of them kind of gathered here. Then when Y is 0, Y hat should also be 0. So we'll also have all of them gathered here. That is the perfect prediction. You should only have 2 points up here and at this point where Y is 0. But you can see that there are some situations where we want to predict 0, but our Y hat is predicting values that are close to 1. And then here we also want to predict 1, but our Y hat is predicting values that are low. Okay. Now, one thing I have to tell everyone is that this will be difficult to predict simply because the values are random. We will never be able to get to predict it. We only have 2 parameters and we have to predict something that's not correlated in any linear manner. A more a better prediction would have been if we actually had like um we had linear values, right? And then we were able to just use a discontinuity to do that. So this will be difficult to predict, but I just want to show you the process of doing it. Now, so we've done the cost, we've done the prediction function. Now we need to do the cost function. So the cost function is again y hat is a negative log likelihood, which you can see here. Let me bring this back down just so that we will remember that it matches. Um, so if you look at this, right, this is, we've translated it, right? Remember 1 over n of the sum, it has to be summation because you have to take each, this is a combined piecewise, a combination of 2 piecewise equations, right? We combine them into a single equation. So this will give you the loss function for a single data point, right? So we don't need to square it, remember, because by using this piecewise combination, we have maximized for each of them. Then we now sum it, right? And then sum it for each data point from I equals 1 to n, and we divide it by n. So this is effectively the mean. That's why we have np dot mean. We could also have done np dot sum divided by n, right? But np dot mean is easier. I don't need to go look for n. Then remember the negative sign because the losses, the errors are actually negative. So, but we want a positive value because it's a minimization problem. So we have to turn it from a negative to positive. So we use this negative sign. And the rest of it is the same thing, right? Y, which is the value of y, times np log y hat, which is the prediction, right? And then 1 minus y, right, times np log 1 minus y hat, which is also the prediction. So that gives you the cost function. And as simple as that,